And good morning to everyone. So our today's lead code question is 1665, which is minimum initial energy to finish task. So basically in this question we are given another task where task of I has two things, actual I and minimum I. So actual of I is basically the actual amount of energy that we have to spend on the ith task to finish it, and minimum of I is basically the minimum amount of energy which we require to begin the ith task. So here it is given an example that 10 and 12. So 12 is the minimum energy. 12 is the minimum energy that we require to start this task, and suppose our current energy is 11, then we cannot start this task. But if our current energy is 13, that means 13 is greater than 12, that is the minimum energy, so we can start this task. And when we complete this task, so our energy is 13, and how much we require? 10 we require, so 13 minus 10, so 3 is left with us, right? So this way we are given an array of tasks, and what we have to do is it is given that we can finish the task in any order, right? And at the end what we need is we need to tell them the minimum initial amount of energy that we need to finish all the tasks, right? So let's start. So let's see some examples to get the question more clearly. So here we are given task 1 2 2 4 4 8, right? So we are starting with 8. We have take energy is equal to 8, right? So first we execute this task, right? So how much minimum energy it requires? 8. So we have taken, so we have sufficient energy to start this task. So when we complete this task, how many energy we are left? We are left with 8 minus how much it requires? 4. So we are left with 4. Now let's execute this task. So how much energy it requires? 4. And how much we have 4. So when we complete this task, how much it requires? It requires 2. So 4 minus 2 is 2. So we are left with energy 2. How much this task require? It requires 2. So how much we have also 2. So how much it requires? It requires 1. So we are left with 1. So with energy is equal to 8, with energy is equal to 8, we have executed all the three tasks. Now let's say suppose we have energy is equal to 7. If we have taken energy is equal to 7, then if we execute this task require minimum energy as 8, and our energy is 7, which is lesser than minimum, so we can't execute this task. So our answer is 8, right? Now let's see this example. So we have again these all the tasks, and now we have to execute all these tasks and find the minimum energy that we require. So here the answer is 32. So let's say we have taken this 32, right? And now we have executed the first task. So now after executing first task, our energy will be 32 minus 1, which is 31. Then we executed second task. So 31 minus 2 is 29. Then we executed third task. So 29 minus 10 is 19. Then we have energy 19, which is greater than 12. So after executing, we are left with energy is equal to 9. Then we have executed this task. So 32 is the minimum energy. 32 is the minimum energy that is required to satisfy both the conditions of minimum constraints, and we have, so that we left with some and we have sufficient actual energy. Let's see the constraints. So the number of tasks that we have can be up to 10 ki power 5, right? So we have to think of some solution of either big of n or big of n log n, right? N log n, because our array length is up to 10 ki power 5, and also actual and minimum values can be up to 10 ki power 4, right? So let's see the approach. So basically each task has two things, actual and minimum, where minimum is the minimum energy that we require before starting a task, and actual is the energy required to complete the task, right? And our goal is to find the minimum initial energy that we require to complete all the task. So now what we need, first we need to find the order of the task in which we can execute that them such that we get the minimum energy E, right? So now what is our goal is to first find the order of the task to execute them. So let's suppose we have two tasks, A and B, right? Where A is the actual energy consumed, m is the minimum energy required. Now what we want to determine, we want to determine whether we execute A before B, we execute A before B or B before A, like in which order we execute them such that we require minimum energy. So let's say we execute A before B, A before B, and suppose our initial energy is E, our initial energy is E, right? So for A we have A1 comma M1. Then to execute A, our energy should be greater than equal to M1, right? That is the minimum condition should be satisfied, right? So after completing A, how much energy we are left? We are left with energy E minus A1 because it will consume A1 energy. Then we have B. So for B we are given A2 comma M2. Now to execute B, the energy that we have, that is E minus A1, should be greater than the minimum, greater than or equal to the minimum, that is M2. So here if we shift this A1 this side, then E should be greater than or equal to A1 plus M2, right? So this is the condition. So if we see the total minimum energy that we need is is maximum of M1 comma A1 plus M2, like maximum of these two, right? So if we execute A before B, then the minimum energy is equal to maximum of M1 comma A1 plus M2, right? Similarly, if we have to execute B before A, if we have to execute B before A, then the minimum energy needed is maximum of M2 comma A2 plus M1, right? M2 comma A2 plus M1, right? Now we have, this is case 2 and the above one is case 1. So which case we will taking, we will take that case which will give us less energy, and we are assuming that we execute A before B, we want to execute A before B. That means the minimum energy of case A, which is maximum of M1 comma A1 plus M2, should be less than minimum energy of the second case, that is B before A, right? So this is the expression that we have got, right? So if you have to execute A before B, then energy that we get in case 1 should be lesser than energy in case B, because our overall goal is to minimize the energy. So the expression that we get from this thing is that maximum of M1 comma A1 plus M2 should be less than maximum of M2 comma A2 plus M1, right? So the important observation from here is, since M1 is always be greater than A1 and M2 will always be greater than or A2, right? And we also know that A1 plus M2 will always be greater than equal to M2, and A2 plus M1 will always be greater than M1, right? So these expression will always hold. So if we see A1 plus M2 dominates the left max means this part. A1 plus M2 will dominate this part, and A2 plus M1 dominates the right part, this part, right? A2 plus M1 dominates this part and A1 plus M2 dominates this part, right? See here, A2 plus M1 will always be greater than this M1, Similarly, A1 plus M2 is greater than M2, right? So here a1 plus m2 dominates this part and a2 plus m1 dominates this part, right? So we compare so instead of comparing this whole equation, what we'll do is we'll compare a1 plus m2 from the left part, a1 plus m2 from the left part, and a2 plus m1 from the right part, right? And then we if we rearrange, so m2 minus a2, m2 minus a2 should be less than m1 minus a1, should be less than m1 minus a1 when if you have to execute a before b. If you have to execute a before b, then this condition, that is m2 minus a2 is lesser than m1 minus a1, should hold if you have to execute a before b. That means m1 minus a1, m1 minus a1 should be greater than m2 minus a2, right? If you have to execute a before b. So what we get from here, we get that the task which has larger minimum minus actual difference, which has larger minimum minus actual difference should execute first, should execute first, right? This is what we get from this thing, right? Because we have assumed that we have to execute a before b, and we are getting the minimum minus actual difference of a should be greater than minimum minus actual difference of 2 if you have to execute a before b, and where minimum minus actual represents the extra energy that is required by the task. So basically, if a task requires huge starting energy but consumes little energy, that means it is restrictive, that means we have to execute it first, right? So we get that the task with minimum minus actual difference, those tasks that has minimum minus actual difference larger should be executed first, should be executed first. So now what we'll do is we will sort our array, we will sort our array based on the difference, based on the difference that is minimum minus actual, to find the order of our tasks, right? So once we sort the array, that means then we get the order. Now what we need to do is we need to find the minimum energy, we need to find the minimum energy required to execute all the tasks, required to execute all the tasks. So now first way is we can use binary search over here, we can use binary search over here, and then find the minimum energy. So it will take n log n time, and log n time, right? For binary search our range will be from 1 to 10 ki power 14. Now how 10 ki power 14? So total elements that we have is 10 ki power 5, and each element can be up to 10 ki power 4, right? So 10 ki power 4 plus 10 ki power 4, which is 10 ki power 5 into 10 ki power 4, which is 10 ki power 9. So maximum range will be 10 ki power 9. So this is a range for binary search. Then we find the mid, and we check whether it is feasible to complete all the tasks with this energy. So if we complete the task with the mid energy, then we search in the left half, right? Else we shift in the right half, right? So this way we will find the minimum energy. So this is method 1, which will take n log n time. The other method that we can opt is, basically we have taken two variables, energy which will store the current available energy with us, and the answer store minimum initial energy that we need. So initially we have declared both as 0, and then what we'll do is we'll process each task one by one in the sorted order, right? So for every task we have two things, actual and minimum. Now if our current energy stored, that is stored in variable energy, is smaller than minimum energy required by the task, that means we cannot start the task, our task, and we have to increase our initial energy, and what we need minimum energy, right? So by how much we have to increase? so we have to increase by minimum minus energy, right? Minimum minus energy, because we have energy and we need minimum. So this difference should be added to energy to reach at minimum, right? So how much we have increased? We have increased by d, so that we will add to the answer, that we will add to the answer, and now our energy will become equal to minimum. So now we have enough energy to perform the current task, right? And after completing this task, our energy will be decreased by actual, because actual is the amount of energy that the task will consume. So we reduce energy is equal to energy minus actual, and this thing we keep repeating for all the tasks. So once again I'll tell you, if our energy is less than the minimum of the current task, then we increase our energy by minimum minus energy and add that particular energy to the answer. And once our energy become equals to the minimum energy that we require, then we complete the task, and our energy will be decreased by actual, right? And once we process all the tasks, then answer will store the minimum initial energy that we require. So we return our answer. So let's try to see how it works. So we have taken tasks 1 2 2 4 4 8. So then first we sort by minimum minus actual difference in descending order, right? Because we have to process those tasks first that has minimum minus actual difference greater, right? So after sorting we get this as the array, and then we have initialize energy is equal to 0 and answer is equal to 0. Now our first task is 4 comma 8. That means it requires a minimum 8 energy to start the task, but how much energy we have? 0. So so we have to increase the energy by 8 minus 0 is 8, so we have to increase the energy by 8. So our answer will be now 8, that is 0 plus 8, and now our energy has become 8, right? Now we have sufficient energy to start the task, so we perform the task. So our energy will become 8 minus 4, so 4 is the actual energy that we have reduced. So now how much energy we are left with? We are left with energy is 4. So now next we move to the next task. So next task is 2 comma 4, and it requires a minimum energy of 4, and we already have that energy, so we directly perform this task. So when we perform this task, how much actual energy it will take? It will take 2. So how much we are left with? We are left with earlier we have 4, this will require 2, so we are left with 2. So now again we move to the next task. Next task is 1 comma 2, and the energy that we have is 2, and it also requires a minimum energy of 2. So we can directly perform because we have the sufficient energy with us. So the energy left after this task is 2 minus 1 1. So we have performed all the task. So our final answer is 8, that is we require a minimum energy of 8 to perform all the 3 tasks. So let's see the code part. So first of all we sort all the task on the basis of the difference minimum minus actual, and in descending order, right? That's why we are d1 is greater than d2, right? So once we get the sorted task, now our goal is to find the energy. So we have taken answer is equal to 0 and energy is equal to 0, and then we execute each task one by one. So we have taken the actual energy and minimum energy of the task. Now if our current energy is less than the minimum energy that we require, then we have to increase our initial energy. So how much we have to increase? The difference of minimum minus energy by which we increase, right? So now we have updated our answer, that we have added the energy that we increase to the answer, and then now our energy is equal to minimum, right? And now we perform the task. So while performing the task, we decrease the energy by actual energy that we require, right? So after processing all the tasks, we return the answer. So I hope I'm able to explain you the solution properly. So if you like the video, please make sure to like, share and subscribe the channel. Thank you.